Hello everybody, welcome into another lesson. So today is going to be the last lesson of the trigonometry series. We are going to talk about applications of right angle trigonometry. So we are going to do 6 word problems that put this into real world practice. Up first, there's a couple terms we need to talk about. The angle of depression and the angle of elevation, because these are going to come up in today's problems. Let's say you're on top of a building here, right? I'm on top of a building and I'm looking down onto the ground. I'm looking out over the horizon. Well, you could say that's a 30-degree angle from the top of the building down to the ground. That's called the angle of depression. It's all based on looking downward. That's the angle of depression. You can remember it as if you're depressed, you're kind of down. So looking down from that top of that building, you have a 30-degree angle of depression. Now let's say I'm on the ground, I'm going to look up at the top of the same building. It's a 30-degree angle from the ground to the top of the building, but I'm looking up this time. If I'm looking up, that is called the angle of elevation. You could think of it as the higher you go in elevation, the higher up you are. So depression, angle of depression is from looking down upon something. Angle of elevation is looking up on something. That's how you can remember those. All right. So I'm going to do a few simple word problems here. Let me write these out. Okay, so we have our very first problem here. This problem reads, when the sun's angle of elevation is 57 degrees, a building casts a shadow 21 meters long. How tall is the building? So what might help first in these types of problems, like in any word problems really, draw yourself a diagram, okay? So we got the building here. We'll draw a nice building. I'll even draw some windows on it, just so we can illustrate that this is a building. Let's draw a nice door on that building. Okay. And then we'll say up here, sure, I have the sun, right? I had the sun right over the building. So it says the sun's angle of elevation is 57 degrees. Really, this should almost be angle of depression because it's casting a shadow to the ground here from the building. It's casting a shadow to the building. It's casting a shadow from the building. The sun's overhead the building, meeting the ground, which causes a shadow to meet here. We'll just scribble this for the shadow, right? This will be the shadow of the building. Well, the angle of elevation here is going to be 57 degrees. The building standing up, we hope it's not leaning. If it's standing straight up, it's going to form a right angle with the ground, right? That would make sense. If it forms anything other than a right angle, it's leaning. You better call an architect and an engineer in there to fix stuff right away. But anyway, what they also give us that the building casts a shadow 21 meters long when you have the angle of elevation of the sun 57 degrees from the building. So that's what this diagram illustrates. Now we want to find how tall is the building. So basically now, once we have our diagram and understand what the problem's asking, we can go ahead and start solving. We have our angle of 57. Let's see, we have an adjacent side of 21 meters, right? Because that's the shadow, it's the adjacent side. The opposite side is the building. That's what we're trying to find. If you are trying to relate opposite and adjacent, you're going to use the tangent ratio. So you're going to set this up as the tangent of 57 degrees is equal to, we'll say the height, which would be h. We'll call the h here the height. In fact, I'll even put an h next to the building because we're trying to find the height of the building. It'd be h over 21. It'd really be 21 meters, but the answer will be in meters. So then to solve for the height, that's going to be equal to 21 times the tangent of 57 degrees. And we're going to get an answer here. We're going to round it to the nearest integer. We'll just round it to the nearest integer. No decimals today. But one thing again about using your calculator, make sure your calculator is in degree mode. Because if it's not, you're going to get the wrong answer. So 21 times the tangent of 57 gives a height of approximately 32 meters. So the building is approximately 32 meters high, which would be over 90 feet high, almost 100 feet high. So the height of the building would be 32 meters, considering all these factors. And I got 5 more problems here. Alright, what's the next one? Whoops. It's good to point out this is a vertical pull, not just a pull. Alright. Whoops, not of the sum. The sum's not in the sky. The sun is. Alright. At a certain time, a vertical pole 3 meters tall casts a 4 meter shadow. What is the angle of elevation of the sun? So once again, let's go ahead and draw ourselves a diagram here. Why don't we draw our pole first? We'll just draw a nice pole here. Alright, so there's our pole. We'll draw the sun overhead. Draw a nice sun there. This is why I never took art in high school or in college, because I was not good at it. So there's the sun, there's the pole. The pole has a height of, well, we'll list that in a second. Of course, it's got a shadow here. The pole has a shadow, right? We're trying to find the angle of elevation to the sun. We're going to try to find that angle of elevation. So, we know the height of the pole to be 3 meters high. We have that. We know the length of the shadow is 4 meters. What we don't have is the angle of elevation. Why don't we call that x? We'll call the angle of elevation x. That's as good of a place to start as any, right? It'll be x degrees. So we're trying to figure out the angle of elevation from the ground where the shadow ends to the sun. Okay. So, we see here with respect to this diagram, we have the opposite leg from angle x being 3 meters and the adjacent leg to angle x being 4 meters. If you relate opposite and adjacent, you use the tangent ratio. So set up your tangent ratio, which would be the tangent of x degrees. That's going to equal the opposite side of 3 over 4, which now, just to get x, you have to take the tangent inverse of both sides. So if you took the tangent inverse function of the left side, you would just get x degrees is equal to the tangent inverse, or arctangent, depending upon what your calculator says. It would be the tangent inverse of 3/4. So then we're going to get an approximate result to the nearest integer for the degrees. So now use your calculator, take the tangent inverse of 3/4, but again, make sure the mode is set to degrees and not radians. Alright, it's approximately a 37-degree angle of elevation. So the angle of elevation from the ground to where the shadow ends up to the sun above the pole is about 37 degrees. I got 4 more problems. Okay, this one. Alright, so here's our next problem. A kite is flying at an angle of elevation of about 40 degrees. All 80 meters of strain have been let out. Ignoring the sag in the strain, find the height of the kite to the nearest 10 meters. Okay. So, you start on the ground, right? So, you're on the ground here for this. The kite originates, of course, from the ground. It's going to flow upward at an angle, right? And then we'll say yeah, there's your nice kite. There's your kite up flying in the air, okay? So you have that. So from the ground to the end of the kite, that is a 40-degree angle of elevation. Now, it tells you that all 80 meters of strain have been let out. So when you start from the ground upward, that's 80 meters of strain for the kite. It's not asking you yet that 80 meters of strain does not tell you how high up the kite is. It tells you how long the kite is. In this case, because it's going upward, the kite is actually, the length of that's going to be your hypotenuse for this right triangle. What they want to know is how high up is the kite currently, which here would form a right angle with the ground, right? It forms a right triangle. We need to find the height to the nearest 10 meters. So we have our kite starting from the ground, going upward, all 80 meters of it. That would be your hypotenuse. The angle of elevation from the ground upward is 40 degrees. What we don't know is the height of the kite itself. So we have here, we're trying to relate, of course, the hypotenuse and the opposite side. If we're relating those two, you're going to set up the sine ratio. So you're going to take the sine of that 40 degrees, set that equal to your height, h, over that hypotenuse of 80. So then the height is equal to 80 times the sine of 40 degrees. So then we're going to get an answer to approximately to the nearest 10 meters. Again, and I don't say this enough, I don't think, I'm sure I do, make sure your calculator is in degree mode, not in radian mode. To the nearest 10 meters, it's about 50 meters. So it's really about 51.42 meters, so to the nearest 10, that's about 50 meters. So the kite is approximately 50 meters off the ground, which would be greater than 150 feet off the ground for my American friends. Alright, I have 3 more exercises here, and then we're done. But yeah, it's actually pretty cool what you can do with trigonometry. And all the things I'm doing with it today, that's not all you can do with it. There's way more to it. Ask engineers and rocket scientists and all that. They'll tell you they do quite a bit with it. Okay. And advertising blimp hovers over a stadium at an altitude of 125 meters. The pilot cites a tennis court at an 8-degree angle of depression. Find the ground distance between the stadium and the tennis court. Alright, so this is a big one. An advertising blimp hovers over a stadium at an altitude of 125 meters. I'm sure if any of you have gone to any ball games, you've seen a blimp that hovers over sometimes. So keep that in mind. The pilot sights a tennis court at an 8-degree angle of depression. Find the ground distance between the stadium and the tennis court. So again, let's set up an illustration here. I'm going to do the best I can for that. That's my attempt at a stadium. That is my attempt at a stadium here. Not the best, but I just draw some things here for the stadium, whatever that is. Overhead. We'll have the blimp up here, okay? We have a blimp and then we got the stadium. It's flying over the stadium. And then we got the tennis court off in the distance here. Good Lord. I would have to pick a drawing lesson. Alright, that's your tennis court. I can't do very well. So we got the blimp flying directly over the stadium at an angle of depression of 8 degrees. Well, you'll get the idea. Somewhere in here, the pilot's looking. 8-degree angle of depression is where they look down, they see the tennis court. We're going to try to find the ground distance from said stadium to the tennis court. So let's establish that we know the angle of depression is 8 degrees. That's going to help us. Now, the height of the blimp over the stadium is 125 meters, right? So it's 125 meters above the stadium. The pilot sights the tennis court at an 8-degree angle of depression where their eyes meet the tennis court. What we're trying to find is the ground distance between said stadium and the tennis court. So, what we have now, we have our angle 8 degrees, we have the opposite side, and then we have the adjacent side. If you're relating opposite and adjacent side, that's going to be the tangent ratio. So set up your tangent ratio for the tangent of 8 degrees. That's going to be equal to the opposite side of 125 over the adjacent side, which is d for your distance. So then d times the tangent of 8 degrees would equal 125. So then the distance equals 125 over the tangent of 8 degrees. which then will get an approximate distance here to the nearest integer once we put that in. But keep in mind, keep your answers in degree mode. All right, 125 divided by the tangent of 8 degrees. It is about 889 meters away. So the ground distance from the stadium to the tennis court is about 889 meters away. It would even be reasonable to say about 900 meters away. If you're in that ballpark, that's fine. So 889 meters, 890 meters, 900 meters, somewhere in that ballpark, you're good. I just got 2 more problems, then we're done. Alright, what is the next one? Alright, so I actually think I'll make this the last problem. I think you guys are starting to get the idea. An observer located 3 kilometers from a rocket launch site sees a rocket at an angle of elevation of 38 degrees. How high is the rocket at that moment? Well, let's start where the observer is this time. Draw me a nice little stick figure. That's about the best I can do for artwork. So there's your observer. Looks upward, right? He sees no. He sees a rocket So he looks up, he sees a rocket, and he's on the ground, of course, at an angle of elevation of 38 degrees. Well, he is 3 kilometers from the launch site. So from him to where the rocket launch site is 3 kilometers. That's your ground distance. The angle of elevation he's looking up at is 38 degrees. What we want to know here is the height of the rocket at that moment. So this time here, we have our angle, we have the opposite side and the adjacent side. So you're going to set up your tangent ratio. So you would set up the tangent of 38 degrees. That's going to be equal to your opposite side with h over your adjacent side of 3 kilometers. We'll just say 3 for a moment. So the height is equal to 3 times the tangent of 38 degrees. So we'll round to the nearest kilometer. So let's go ahead and do that. So 3 times the tangent of 38 degrees. It's going to be approximately 2 kilometers up. It's approximately 2 kilometers in the sky. It's actually more than that, but rounding to the nearest kilometer put it at 2 kilometers. So that's over a mile high in the sky from where he's at. He can see that. So this has been it for applications of trigonometry, and actually it for doing right triangles and trigonometry altogether. Next lesson, we'll start a 7-lesson unit on circles. The very next lesson will be basic terms and definitions of circles with a little bit of some problems. So stay tuned for that. I hope everyone has a great night. Take care.